Right, this actually brings us back to the thing I said I was going to talk about briefly, which is why the notation A, B makes sense for intersections of two things. So if you think of this as a function that is equal to 1, so if we represent, there's this notion of indicator functions. We're going to write IA of some number, of some value x is equal to 1 if x is in A, and it's equal to 0 if x is not in A. So this is the membership function or indicator function of the set A. Okay? So similarly, IB would be the function that takes the value 1 for elements of B and takes the value 0 for things that aren't the elements of B. Okay? So what is the indicator function of the intersection AB? So the indicator of AB is equal to 1 if x is in A intersect B, and it's equal to 0 if x is not in A intersect B. Okay? I want a function that's equal to 1 if x is in the intersection of A and B. Well, what happens if I multiply together the membership function of A and the membership function of B? So I have IB of x is equal to 1, x is in B, 0 otherwise. Okay, IA times IB is going to be equal to 1 if x is in both A and B. And otherwise, it's going to be equal to 0. Because if either of these is 0, if you're not in A, then IA is going to be 0. 0 times whatever this is going to give you 0. If you're not in B, then this is going to be 0. 0 times whatever this is going to give you 0. You're only going to get 1 if you're in both of them. So IAB is, in fact, equal to IA times IB. And this is why this sort of multiplication notation for intersection makes sense. Because the membership function, the indicator function for the intersection, is the product of the indicator functions for the two sets separately. Again, this is just a cultural nuance. You don't have to remember this. It just might help you understand where the notation comes from.